today we are going to see about Proell Governor. Alright, so here you can see the parts of the Proell Governor. Right? So there are different parts. So these are the fly balls which are going to fly while this part rotates. Right? So this complete assembly will rotate, and during that time, this flywheel will move either outwards or inwards. Right? And this is the arm, right, which will extend and contract. As already here is the link. This one will either expand or contract, and this is a center load, or you can call it dead weight, right? So this will either raise up or fall down, right? Depend on the motion of these arms and links, right? Depend on this motion. So here see, this is the median position, and this is the maximum position of the sleeve, and this is the minimum position. When the sleeve move here, this is the minimum position, right? So here is the minimum position. So up and down movement of the sleeve makes the lever rotate to actuate the valve. So here you can see when this sleeve move up and down, this connection make this valve to either close or open, right? So there you can see when it moves up, it's open. Sorry, closed. When it's moved down, it's open, right? So when the arm expands, links pull the sleeve upwards, right? So when you can see when this arm expand means coming outside, right? When it expand, it pulls the sleeve upwards, right? So this sleeve will move upwards. When this arm contract, right? When this arm contract, this sleeve will fall down, right? You can see this motion. So when it's expand, it move up. When it contract, it falls down, right? So based on this motion, this will activate this valve, right? So when it activates this valve, this will either open or close, and thereby it will regulate the flow of the working fluid. So here is a flow out, right? So it will regulate the flow of the working fluid, right? So there you can see sleeve pulls up and pushes down the lever using the fork pin, right? So this one either pulls up or push down based on this motion. Fork pin slides freely in the groove, right? So here you can see this may sleeve in the groove, right? So this one will sleeve in the groove on each side provided by the balancing. Okay, so there you can see the fork pin which is sliding, right? So here you see it's sliding. All right. Spline key slides freely up and down in the spline slot cut in the main shaft. Right, so this is a spline shot you can see. So this can slide freely up and down. Okay. So when it rotates, right? When it rotates, you can see. Okay. So here is a bevel gear. This one is connected to the engine shaft. So when the shaft rotates, this gear will rotate, which will rotate this complete mechanism. Right? So during that time, when the speed increases, arm expand due to centrifugal force produced by the rotating fly balls. So due to the force produced by these fly balls, what will happen? The arms will expand. Okay, the arms will expand. Arm contracts and comes down due to the weight of the fly balls and the center load. Right. So when the speed decreases, this arm will contract and this sleeve will fall down. All right. So here is the shaft. Input speed from engine that is to be controlled is applied to the input shaft using the pulley and belt, right? So here is the input. So based on this input, we need to control the fluid, right? Working fluid. So if the speed increases, then this need to be closed to reduce the working fluid. If the speed decreases, this need to be open to increase the flow of the working fluid, right? So when engine speed increases, arm expands and pull the sleeve upwards, right? So here is a position where the speed is high, right? Why? Because the arms are expanded and the sleeve is on the top, right? So this position is actually the speed is high, which in turn rotates the lever so close the valve to decrease the output flow. So there you can see, right? The output flow is almost about to be closed, right? So this passage is so low. Right? This passage is so long. You can observe when this sleeve falls down, right? This will move up and which will open this one so that more amount of oil can flow. Right? So there you can see when it falls down, it opens up so that more amount of working fluid can flow. Right? So valve closes to decrease the output flow. Where you see when the speed is high, this one close to reduce the output flow. When the speed is low, it opens. Right? So this is how the Proell governor works. Right? So when the speed increases, the valve closes to reduce the flow. When the speed decreases, the valve opens to allow more amount of fluid to flow. Right? So this is how the working of the Proell governor is. Right? So you can see it clearly. Alright. So this is actually a dead weight type governor. Dead weight type. So we know there are two types of governors. One is spring controlled and the other one is dead weight type. Right? So this one you see it's a dead weight type governor. Okay, it is a loaded dead weight type. Why do we call like that? Because there is a weight, dead weight on this, which will move up or down. Right? There are no any springs attached to it. Alright. So that's why it's called as a type of dead weight governor. Here fly balls are attached to the link extension in a vertical manner. Right? So there we have already seen it's attached in a vertical manner. Right? So when it moves up, it expands. When it moves down, it contracts. It also has a simple rotational sleeve. The load moves up and down along with the sleeve on the main spindle. Right? So here is our main spindle. It will move or down along with the main spindle. Right? This additional downward force increases the speed of required to enable the bolts to rise to actuate the valve. So based on the motion of this ball and thereby this sleeve and thereby this lever, this valve is activated. Right? So based on the motion of these mechanisms, this valve is activated. So here you can see speed variation occurs when there are changes in the load. So we know that, right? Speed varies with the load. If the load increases, speed decreases. And if the load decreases, speed increases. Right? When the load of the engine decreases, the speed decreases. So what should we do if the speed decreases? We need to increase the speed. To increase the speed, what should be done? The working fluid supply should be high. Right? So hence, the supply of the steam should be increased to reach the set speed limit. So if the speed decreases, this is how it regulates the speed. On the other hand, when the load of the engine decreases, so we know the load of the engine decreases, what will happen? The speed increases, right? So if the speed increases, what should be done? The speed should be reduced. If the speed is to be reduced, what should be done? The working fluid supply should be reduced. Right? So and hence the supply of the steam should be decreased to reach the set speed limit. Right? So you can see this is the function of this governor, especially the Proell governor. The governor automatically controls the supply of engine fluid to the engine with the varying load conditions and keeps the mean speed within the set limits. So if you can see in the working animation motion diagram, there is a maximum and minimum diagram, right? Maximum and minimum speed it can achieve. So the sleeve, if it is here, that is minimum speed, and if it is here, that's the maximum speed because that's the only region this sleeve can move, right? This is the only region the sleeve can move. And here are the other parts. So this is connected to the input shaft, alright? So here are the bevel gears which are connected to the sleeve, alright? And here is the lever which is connected to the throttle valve, alright? So this is how the Proell governor functions. The Proell governor has the balls fixed at B and C to the extensions of the links D, F, and EG, right? So as you can see in the picture, right, you see here, all right? So here we have ball B, and here we have ball C. They are fixed to the extensions of the links DF, right? So DF, this is one link, and EG, this is another link. Right? So to the extensions of these links, these two balls are fixed. The arms FP and GQ, right? The arms FP and GQ are pivoted at P and Q respectively. They are pivoted at P and Q respectively, right? So we'll see how to find the equilibrium. Consider the equilibrium of the forces of on one half of the governor as shown in this figure, right? So usually what we do, we take for only a half, right? Because the other side is going to be also the similar to that of the other half. So we'll consider only one half while solving such things, right? So we'll consider only this half. Okay. The instantaneous center I lies on the intersection of the line FP produced and the line from D drawn perpendicular to the spindle axis, right? So we have an arm here, right? FP, right? So to the line extended from this sleeve, right? That is PFI, this line, and the line which is drawn perpendicular to the spindle axis. So this is our spindle axis, right? So this line is drawn perpendicular to the spindle axis, that is DMI, right? So this line. So the point where they two meet is the instantaneous center I, right? So the line PFI and the line DMI, they meet at a point I, and this I is the instantaneous center, right? The perpendicular BM is drawn on ID. Perpendicular BM is drawn on ID. Okay. So why do we draw this BM? In order to find the angles. Why? Because here we have an angle alpha, right? The FP makes an angle alpha with the axis, and here we have another angle beta. So this beta is the angle formed with the axis by DF, right? So in order to accommodate these two angles here, we make this perpendicular, right? So this is alpha with the spindle, so this is also going to be alpha, right? Allied angle, and here this is beta and this is beta. Why? This is alternate angle, right? This sleeve and DF is beta, therefore DF and MF is again beta because it is alternate angle, and here this is alpha and here is also alpha. This is allied angles, right? So in order to accommodate these two angles, we draw this perpendicular BFM, right? BFM, this perpendicular. Okay. So this is easy to take momentums, right? So we'll see. We'll first identify the terms. So small m, mass of each ball in kilogram, right? So here we are going to have small m, which would be the mass of each ball, and therefore W, small w would be the weight of the balls, right? That is mg. Right? W is the weight of the ball, mg. And capital M, mass of the central load in kilogram, right? So capital M would be mass of the central load, and therefore W would be weight of the central load, right? So here W by 2, why? Because we are taking only half to solve, right? So the other half will have the W by 2, so that would be W. Okay. So now we take only half of the image to solve the numerical, so that is W by 2, that is capital W, and here for the ball that is small w. Okay, so these are the weights. Then R, radius of rotation in meters, right? So R is the radius of rotation, okay, between spindle and ball. Then we have H, height of the governor in meters, right? So as normal notation, we have the H, that is the height of the governor, okay. And then we have N, speed of the balls in RPM, okay. So N, speed of the ball in rotation per minute, RPM. And therefore omega is the angular speed, right? So how do we calculate it? 2 pi n by 60, right? So this n is the RPM, 2 pi n by 60 radian per second. And then we have alpha, angle of inclination of the arm or upper link to the vertical, right? So angle of inclination of the upper link to the vertical is alpha, and similarly angle of inclination of the lower link to the vertical is beta, right? Angle of inclination to the lower link to the vertical is beta, right? So these are the terms we are going to use here, right? Now we'll take moment about I, right? So this is our instantaneous center. So how we'll solve? We'll take moments about I, right? So you can see we have a force here, right? And we have a distance between that force and the moment point of this momentum, right? Similarly, we have another weight here, right? This is another force. So the distance between that is also given, right? So that is Im, all right? And we have another weight here, and the distance between that is also given, right? So now we'll try to fix it in a equation to find moment, okay? So you see here Fc, right? That is force, right? Centrifugal force, Fc, centrifugal force, into, right? So this is the way the force act. So the distance between the point I to this length, how much is that? Bm, right? Bm. So this is Bm. So force Fc into distance Bm. So this is anticlockwise, right? So if I take moment about I, this is anticlockwise. But this W is in clockwise, and this W is also in clockwise direction, right? So we will consider, so this F, this W is in clockwise direction, right? This moment, and this W is also clockwise direction, right? But this Fc is in anti-clockwise direction, right? This is opposing the motion, right? So this is anti-clockwise direction, and this force W by small mass is in clockwise direction, and the weight by larger mass or mass of sleeve is also in clockwise direction, right? So this is clockwise direction, this is clockwise direction, but this is anti-clockwise direction. So when we fix it in moment, okay, so force Fc into distance Bm will be equal to, right, small w, right, small w into distance Im, right? Small w is acting this way, into distance Im plus capital W by 2 into distance Id, right? So capital W by 2 is acting this way, distance is Id, okay, right? So this W's can be replaced by mg, right? So here mg into Im plus W by 2 can be replaced as mg by 2 into Id, right? So this is our equation. So we'll now solve it, okay? So Fc is equal to, right, we are making Fc a subject now, mg into Im upon Bm, right? I'll divide the entire equation by Bm, right? So mg into Im by Bm plus mg by 2 into Id upon Bm, right? And this ID, right, this ID can be written as Im plus Md, right? ID can be written as Im plus Md, okay? So Im plus Md upon Bm, okay? So Fc now can be written as this format, okay? Because ID is equal to Im minus Im plus Md, okay? Multiplying and dividing by Fm. So now what we are doing, we are multiplying it by Fm in order to bring the alpha and beta, these are known terms, right? So we have to somehow bring those terms into the equation, right? So in order to do that, we are now trying to adjust the equation, okay? So we are just trying to adjust the equation, all right? So Fc is equal to, I'm multiplying and dividing by Fm, right? So Fm into, right, mg plus Im upon Fm, right? Mg, right? We have mg, and I take this Bm outside, right? So Fm upon Bm, I take this Bm outside the bracket. So now we have Fm upon Bm within bracket mg into, we already had Im. Now I am dividing it by Fm. So mg into Im upon Fm plus mg by 2, we have mg by 2 here, right? I have already taken this bm outside, right? I have already taken this bm outside the bracket, so within bracket we have im plus md, right? Now I am dividing it by fm. Okay, so what we have, im upon fm plus md upon fm, right? So why did we do that? In order to bring the term alpha and beta inside. So we'll simplify it. Fm upon Bm, that already we have mg into Im upon Fm, right? So if we take Im, it's here, upon Fm, Fm it's here. So this is tan alpha, right? We know tan alpha is equal to opposite over adjacent, right? So that is Im upon Fm. So instead of Im upon Fm, I will put tan alpha, right? So mg into tan alpha plus mg by 2 into, again, here we have Im upon Fm. So Im upon Fm. So that is opposite over adjacent. So opposite over adjacent is tan alpha, right? Opposite over adjacent is tan alpha. And then we have md upon Fm, right? So we have md here, right? md here, Fm here, okay? Again, opposite md upon adjacent Fm, that is tan beta, right? We know tan is opposite of adjacent, so md upon Fm, that is tan beta. So we have tan alpha plus tan beta here, right? So when we simplify this, we have Fm upon Bm into mg tan alpha plus capital Mg by 2 tan alpha plus tan beta. Okay. So now I will take this tan alpha outside the bracket. So here also we have tan alpha, here also we have tan alpha. I'll take this out. Okay. So Fm upon Bm into tan alpha within bracket. Since I have taken this tan alpha outside, we have only Ng here plus Mg by 2 into, we have already taken this tan alpha out, therefore 1 plus, we have tan beta here, I taken out tan alpha, therefore divided by tan alpha. Okay. So now we wrote this into this format, right? This is just adjustment. We didn't do any extra things, right? Just adjustment. We know that Fc is equal to mr omega squared. So centrifugal force Fc is equal to mr omega squared, that we know. And tan alpha is equal to r upon h, right? So tan alpha we have already seen, that is radius r upon h, right? Tan alpha, right? This tan alpha is equal to radius r upon length h or height h, right? So we can replace it by r upon h. Okay. So tan alpha is equal to r upon h, and q is equal to tan beta upon tan alpha. So in the previous governor also, Porter governor also, we have seen this q is equal to tan beta upon tan alpha, because in order to reduce the complexity, because otherwise we have to keep this tan beta upon tan alpha thing throughout the solution, right? So in order to just reduce the complexity, we'll assume q as a replacement for tan alpha, tan beta upon tan alpha, right? So you can take a, b, c, or whatever it is, we'll just take q, right? So q is equal to tan beta upon tan alpha. So taking these assumptions, I will rewrite this form equation. So Fc, we know mr omega square, right? Fc is equal to mr omega square equal to Fm upon Bm, right? Fm upon Bm into tan alpha, I told you, that is r upon h, right? Tan alpha r upon h. Within bracket, we have mg, right? We have mg plus mg by 2 into 1 plus tan beta upon tan alpha, that is q, right? So that is 1 plus q, all right? And therefore omega square is equal to, so now we have mr omega square here. So I'll divide the entire equation with m and r, right? So we will left with omega square. So omega square upon omega square equal to Fm upon Bm, that's here. We have r upon h, but I have already dividing it by mr, right? So therefore this r and that r would be cancelled out, but we will be having only h on the bottom, right? H. And we have an mg here, okay? So m we have taken inside, and g we put outside. Why? Because here also I have a g, here also I have a g, so I'll take it outside. So m plus m by 2 into 1 plus q, right? And this m I have taken from here, right? Why? Because we are dividing it by mr, so r and this r cancelled out, this m will come down, so that is this m, okay? and I take this G outside. So here I have a G, here I have a G. I take this G outside. So that is G upon this H is already outside, right? So I simplified it by writing FC as MR omega squared and tan alpha as R upon H and Q as tan beta upon tan alpha. So I just simplified it. Substituting omega is equal to 2 pi n by 60, right? So we know omega is equal to 2 pi n by 60, right? So that is omega is equal to 2 pi n by 60, and G will replace it by 9.81 meter per second squared, right? So when we replace it, we will be having, instead of omega squared, I will be replacing it by 2 pi n by 60. So 2 is a numerical value, pi is a numerical value, 60 is a numerical value. So when we solve it, we will be leaving out with n squared, right? So n squared is there, equal to Fm upon Bm. We have Fm upon Bm into m plus m by 2 into 1 plus q, right? M plus m by 2 into 1 plus q upon m into, we have G upon H here, right? So H is there. G I replace with 9.81, and here I have 2 into pi 3.14 by 60, right? So once we solve everything, I will be having a 895, right? So if you remember, we have seen this 895 previously also in the Proell Governor as well as in what Governor, right? So that is 895 upon H. So Fm upon Bm within bracket m plus capital M by 2 into 1 plus q upon m into 895 by H, right? So this is how we find the n squared ORPM in Proell Governor. Okay. So if any other quantity is asked, you can make that quantity as the subject, right? Say for example, if R is asked or if H is asked, right? You can make that quantity as subject and you can solve it, right? So this is how we solve if a numerical is given in Proell Governor, right? Proell Governor.